Okay, so welcome to this year's Robert F. Christy Lecture. This lectureship celebrates the life and work of the late Robert F. Christy, and we're very happy we're joined today by his wife, Juliana, his daughter, Yulia, and grandson, Kelso. And there may or may not be other family members on Zoom. Didn't see them.
Now let's try. There we go.
Okay. Yeah, so you'll notice that Robert got his bachelor's degree at UBC at the ripe old age of 19. That's explained by the fact that when he was in middle school, he won a gold medal, which allowed him to go directly from middle school to university, skipping all the high school nonsense. And that gold medal was also important since he had been orphaned at the age of 10, so the money was much appreciated. So after UBC, he went with his UBC friend, George Volkoff, to Berkeley to work with Robert Oppenheimer. All the LIGO folks and astrophysicists will know about the Tolman-Oppenheimer-Volkoff equation and maximum mass of the neutron star. But Christy's PhD was not on that. It was on the theory of muon spin and muon showers. And at the time, most people had thought the muon was the Yukawa particle that mediated the strong interaction, but he showed that in fact it could not be. It wasn't spin one, didn't have strong interactions, and that was the pion that was discovered 6 years later. You also notice that Robert Christy was employee number 14 of the Manhattan Project. He joined it before he was a US citizen. They only sort of decided, well, maybe we better make it a US citizen a year later. He was responsible for the fact that theoretical calculations were actually trusted by the experimentalists because he predicted the mass of uranium-235 that would be needed for the first reactor to go critical, and he got said 575, it was measured at 565, and after that there was more belief in theorists, and in particular he was responsible for the design of the plutonium core that was exploded at Trinity and then Nagasaki. Now, Oppenheimer at the time was the professor of theoretical physics at Caltech, but after the Manhattan Project, he had too much work in Washington, so it was more convenient for him to go to Princeton, and he recommended his student Christy to be his replacement at Caltech, and that was very good for Caltech. So he worked, was sort of quite active and campaigned for atmospheric testband treaties and other things after the war. But in 1960, he got interested in Cepheid variables and RR Lyrae stars, which pulsate in and out. And he thought, their radiation, their hydrodynamics, I learned about that, making other things that go just outwards rather than in and out. Many years ago, so maybe I can do the same thing for stars and figure out how they work. He did do that, was elected to the National Academy of Sciences and got the Eddington Medal of the Royal Astronomical Society for his work explaining the Cepheid variables. So here's some thoughts from some of his papers. And he thanks Oppenheimer for the work, for the sabbatical, which enabled him to do this work in Princeton, and for giving him the opportunity to learn about radiation hydrodynamics and numerical methods. For the graduate students here who complain about their computers aren't powerful enough, I should just point out that these pioneering calculations were done on an IBM 7094, which contained the first transistors as opposed to vacuum tubes, and was approximately 10 to the minus 5 of your current cell phones in memory and CPUs, so on. You'll notice the PDV is not lines, but there's a little bit of work. So the star does more work expanding and less work in contracting. So there's a heat engine operating, and that's what makes the stars oscillate. And that was what he convincingly showed, including shocks and everything else that were only included very much later. And so after that, in 1970, he became the vice president and provost at Caltech. He also married Juliana, and somewhat connected to that is the fact that during that period, the first women were allowed to get Caltech, and the first woman faculty member, Olga Todd, was appointed at Caltech. And that's also the time when I was an undergraduate, so I started as an undergrad under Harold Brown. But Jimmy Carter appointed Harold Brown Secretary of Defense. And for those of you familiar with modern Washington, I should point out that Carter nominated Brown for Secretary of Defense on January 20th. He was approved by the Senate on January 21st, and he started work on January 22nd. So if you've seen the way modern Washington works, it's quite a change. So after 1986, he retired from Caltech, and I remember my last conversations with him were about his work on nuclear dosimetry, led to the agreement with Japan on the nuclear dosimetry of the people in Japan who'd been exposed to the nuclear weapons. And I just wanted his favorite hobby. So I should explain that Oppenheimer lured Christy to Los Alamos by promising a half share of a horse. And the other half of the horse was owned by Lloyd Williams. And they used to have long arguments about which of them had the front half of the horse and which of them was the horse's ass, so to speak. But anyway, later in life, he got whole horses for himself and his family members and didn't have to have these arguments anymore. And he was still jumping horses at the age of 93, I understand. Okay, so in light of Bob Christy's pioneering work on numerical calculations and stellar oscillations, it's very appropriate that today we have the person most responsible for the modern state of that an exciting and explosively growing field, Professor Richard Townsend, the Fluno Bascom Professor and Chair of the Astronomy Department at University of Wisconsin-Madison. Professor Townsend got his BA in physics at Oxford in 1994 and his PhD from University College London in 1997 on non-radial pulsations and early type stars. Then he spent a year teaching high school in Ghana. Then he went back to a postdoc at UCL, then at the Bartol Research Institute in Delaware, and then joined the faculty at Wisconsin-Madison in 2008. He's widely known around the world for his work on oscillations of massive stars, their rotation, their mass loss, their magnetic fields, his work with observers on those phenomena, and pioneering computational approaches. But most astronomers will know of Rich for his leadership in two state-of-the-art open source codes. So the first is MESA, which is used to compute the structure and evolution of stars. And any astronomer who installs MESA, almost certainly first thing they do is go to Rich's website and download the MESA SDK. Otherwise, you'll spend 6 weeks of your life trying to get all the software to work. But the second more important piece of software is Gyre, which I think I don't have a hat for that. There are stickers available, which Rich conceived in 2012 and has since led the development of. And Gyre has really revolutionized and democratized also the calculation of both adiabatic and non-adiabatic stellar oscillations and the tidal responses of stars to tides. And Gyre wasn't just a matter of coding up some standard algorithm and putting it on the website, but it's involved development of entirely new methods like contour methods from the complex plane and high precision shooting methods and deep understanding of the gridding, because unfortunately the theory of stellar oscillations has a long history of spurious results due to bad grids, bad codes, and so on. So with the data from the recent Kepler-Corot spacecraft, the current TESS mission, and the upcoming ESA-Plato mission, precision measurement of stellar oscillations are giving entirely new insights into the properties of an interior structure of stars, and together with Gaia, inspiring a real renaissance in astronomy and astrophysics of stars. So it's a pleasure to welcome Professor Townsend, tell us about asteroseismology and wave transport.
Thank you very much, Sterl. That was a lovely introduction, both to the life of Robert Christy, but also to how I fit into the picture in some regard. I'm going to see if I can actually figure out how to get PowerPoint up whilst craning my neck over here. See if I can dig it out. Okay. And I'm not sure the right screen is being shared. Can someone in chat tell me whether they're seeing my slide sorter or whether they're seeing my, or someone online?
I see the yellow.
Okay, I'm seeing some thumbs up, so I'm assuming everything's going all right. Okay, so I'm Rich Townsend. I'm really happy to be here today. It's my first time in Caltech. I've clearly brought the English weather with me. Back in Wisconsin, it's 90 degrees. My family's enjoying the sunshine. Before I left, I wanted to get a photograph of a plant in bloom. And had I waited till I'd come here, I would have had plenty of opportunities. That's the only thing I could find in bloom in Wisconsin at this time of year. And this is a crocus that came up in our front yard. And I wanted to use this as a metaphor for how the study of stellar oscillations as a field has really bloomed since the early days in the 1960s, where Bob Christy was pioneering an understanding of why Cepheid variable stars pulsate. I had only a very brief intersection with Bob at the 2009 Los Alamos Stellar Pulsations Conference, where there was a celebration of Bob's life and contribution to the field. So on the left-hand side there, you can see Bob and Juliana, and then in the middle, you can see, I don't think you can see very much at all. Okay. I'm not sure why it's gone blank. Do we have any technical? Seem to have lost video. Okay. Log in.
Send it just straight to the projector instead.
Okay, that looks promising. If a little different in shape. Okay, fingers crossed. Okay, yeah, so there's me. That's when I just started as faculty at the University of Wisconsin-Madison. I was actually working mainly on magnetic massive stars then, but since then I've transitioned back to stellar oscillations, which is what I've done my thesis on. I've also increased the amount of hair and the amount of mass that is attached to my body.
They lost it on Zoom.
Okay, let's see if I can get the screen sharing going again. Sorry about this. Okay, we got it back. Okay, so let's see if I can get rid of that annoying message. There we go. So a lovely quote from Bob Christy that was recorded in his biography, Achieving the Rare by Juliana, was that of all the fields of research that Bob had been involved in, variable stars was his favorite. And I'm very much in a similar camp, although a stature somewhat a couple of orders of magnitude sort of lower, in that stellar oscillations is absolutely fascinating to me, and it's an area that I absolutely love. Let me give you a brief overview of what I'm going to talk about today. I'm going to cover kind of where Sterl left off with a brief review of the Cepheid variable stars. Then talk about how things started to change in the 60s with the emergence of helioseismology. I'll dip in a little bit into the theory of stellar oscillations, and then I'm going to really transition on to asteroseismology, which is applying the techniques of helioseismology, but to stars other than our own sun. And I'll finish up with a brief discussion of wave transport phenomena, which I think is where the future of the field lies. Before I go any further, I'd like to make a brief shout out to members of my research group back in Madison, or the sort of larger diaspora. Jacqueline Goldstein, who was a grad student and a postdoc, and she's now at MIT. Tanvi Kulkarni, Rihanna Kenzie, and Oscar C. Garcia, who are undergrads working with me. Jarrett Rosenberg, who's my current grad student, and then Meng Sun, who was a postdoc with me a couple of years ago and is now at Northwestern. And a lot of the stuff today that you're going to see that's linked with MESA and with Jaya is thanks to the work done by this team. So the story of stellar oscillations kind of begins with the variable star Delta Cepheus. So Cepheus is a rather nondescript constellation that's over on the other side of the North Celestial Pole from the Big Dipper. And it's been known for hundreds of years that this star is a periodic variable. It changes its brightness on a time scale of a little over 5 days. And the reason it's doing this is the whole star is pulsating. It's oscillating inwards and outwards. And as part of these oscillations, its surface area is changing and the color of the light it's giving off is changing. This up here is a light curve of the star in various different color bands. Delta Cephei is seen as the sort of quintessential example of a radially pulsating star, and it gives its name to the whole class of variable stars called Cepheid variables. Cepheids are celebrated for astronomers and celebrated by astronomers who aren't just interested in stars, because it turns out that the period of a Cepheid depends on its luminosity or vice versa. So if you can measure the period of a Cepheid variable, you can figure out its intrinsic luminosity, and by comparing that to its apparent brightness, you can determine the distance to the Cepheid. This period luminosity relation was discovered at the beginning of the 20th century by Henrietta Swan Leavitt, and it's now named after her as the Leavitt law, and it is one of the fundamental building blocks to measuring the cosmological distance scale in the universe, for getting the distances out to nearby-ish galaxies. So back then, we kind of understood empirically that there's a correlation between the period and luminosity of Cepheids, but we didn't really know why. And the question of why they oscillate was first sort of considered and answered by Eddington in his book, The Internal Constitution of the Stars, where he pointed out that in a star, we have an enormous amount of energy that's generated in the core by nuclear reactions and makes its way out to the surface of the star. And if we have some way of tapping into that energy flow, we can set up a heat engine that converts heat into work, so converts thermal energy into mechanical energy. If we imagine the material in the outer parts of a star undergoes a compression and a rarefaction cycle, and we plot the path followed by the material in the pressure volume plane, if the area enclosed is non-zero for a clockwise cycle in the plane, then we're going to convert some amount of heat into work, and we're going to be running a heat engine. This is fundamentally why Cepheids pulsate. There is some kind of heat engine operating them, operating within them. And Eddington pointed out that the final piece of the puzzle is just figuring out what the valve is that adds heat to the stellar material when it's at maximum compression and maximum temperature, and removes heat when it's at minimum temperature. And if we can set up a valve that takes care of the energy transfers in this way, then there'll naturally be a self-sustaining instability, a sort of heat engine. So it turns out in Cepheids, the valve is the temperature dependence of opacity. So in the 50s, working in the Soviet Union, Zavakin pointed out that the dependence of opacity on temperature or on compression of the material in the second helium ionization zone of stars would have exactly the properties we want. So this graph here is a plot of the rate of change of the opacity with respect to pressure for an adiabatic compression as a function of position within a Cepheid variable model. This is in fact a model with 10 solar masses as its mass, and we're using temperature as a coordinate to say where we are within the star. So the second helium ionization zone occurs at a temperature of a few tens of thousands of Kelvin, and we have this pronounced bump in the opacity derivative. That means when we compress the material in that location, the opacity will go up. It'll dam the further escape of radiation from the star, and so that radiation will instead get deposited as heat in the star locally, and it'll eventually cause the stellar material to expand, cool off, the opacity will go back down, the heat can now escape. And so this is the valve that Eddington had envisaged in his original picture. So Zavakin sort of postulated in a somewhat hand-wavy way in the 50s that the second ionization zone of helium was key to this. But it wasn't really until the 60s when Bob Christy ran hydrodynamical simulations with a lot of the important physics in them that it turned out, yes, this mechanism worked, but there were lots of complexities to it that kind of were missed in the original conception by Zavakin. So we have a lot of nonlinear processes going on. We have propagating ionization fronts and things like that. And it turns out in more recent years that there are even further wrinkles to the problems of why Cepheids pulsate the way they do that concern how the pulsations interact with the convection that occurs in the outer parts of these stars. So Cepheids are actually quite a complicated system to understand. And Bob Christy was well ahead of the curve in the 60s with his initial models. The oscillations I'm going to tell you about for the rest of my talk are kind of somewhat simpler, although the theory behind them is a little bit richer. So I actually don't work on Cepheids myself because I regard them as a little bit too complicated. They're the tough case. So in the early 60s, around about the same time that Bob Christy was working on Cepheids, it was discovered from measurements of velocity fields at the surface of the sun that there's a kind of periodicity there, that stuff seems to move around on a characteristic timescale of 5 minutes, 300 seconds. And this discovery was actually first announced by people working at Caltech, Leighton, Noyes, and Simon. And here is the, I guess my pointer's not showing up there, so I can do it up there. There we go. There's the 5-minute period. So there was clearly some sort of wave-like phenomenon occurring on the surface of the sun. And as subsequent observations came in, a clearer picture slowly emerged. So this is based on observations taken in '68 by Fraser. And this is a plot of where in parameter space most of the power was. And the big peak you see in the sort of top left, so this is at relatively short spatial wavelength. So the x-axis is the spatial wavelength of the variability. The y-axis is the frequency. So at a frequency corresponding to about 5 minutes and relatively short spatial wavelengths corresponding to, well, actually, no, sorry, these are relatively low wave numbers. So these are relatively long wavelengths, wavelengths of about 10 million meters. That's where the 5-minute oscillation of the sun seemed to be found. And as observations improved, it became clear there wasn't just a blob of variability at these wavelengths and these frequencies. There were actually distinct ridges where there seemed to be excess power. And if we look at the same observations using modern instrumentation, so this is with the Michelson Doppler interferometer on the SOHO spacecraft, you can see very, very well-defined ridges of sort of enhanced power. So what are we actually seeing here? Well, these are the normal oscillation modes of the sun. And we're actually picking them up by detecting velocity fields and brightness variations on the sun's surface. These oscillation modes are being excited stochastically, so not as a heat engine as in Cepheids, but stochastically by the convective motions that are going on just below the sun's surface. So the outer 30% of the sun is in a state of turbulent convection, and these convective plumes, these rising and falling fluid elements, actually deposit mechanical energy into the sun's normal oscillation modes and cause these waves we see on the surface. And the presence of these waves has allowed us to study the internal structure of the sun in just the same way that a seismologist on Earth will study the Earth's internal structure by studying earthquakes. And some of the things we've been able to find out include a precise measurement of the sound speed throughout most of the sun's interior. And so this graph on the left is actually a plot of the sound speed error between our best model for the sun and the empirical measurements determined from helioseismology. And we're down at the sub% level. So we know the sound speed throughout the sun to better than 1%, which is incredible. We also know the internal rotation of the sun, shown in the right-hand panel. It turns out that throughout the sun's convection zone, the rotation is differential. The poles of the sun's convection zone are rotating slower than the equator. But interior to the convection zone, in a radiative region, inside about 70% by radius of the sun, the rotation is almost solid body. We still don't fully understand why, but it may have something to do with wave transport, which I'll talk about at the end. Now, I'm not going to say much more about helioseismology, but when I was a grad student, I remember reading about this for the first time, that we're able to map the internal structure of the sun by studies of its surface manifestations of its oscillations. And I thought it was just incredible, wonderful, but I couldn't imagine for the life of me how it might possibly work. How is it we're able to make these measurements and infer the internal structure? What I'm going to do now is take you through a little bit of the theory of stellar oscillations to at least make it more plausible to you why helioseismology and its application to stars, which is asteroseismology, why these techniques work. My talk is not going to have too many equations, but it is going to have a few equations because, goddammit, you're Caltech and you should be able to deal with this. Okay, so the starting point is a spherically symmetric star in hydrostatic equilibrium and thermal equilibrium, and we subject it to small perturbations about a background state. And when I say small, I mean small enough that we can neglect terms of second or higher orders. So we're doing a linear perturbation analysis to a hydrostatic spherical background state. We can develop a set of linearized equations based on the fluid equations. At the top, we have the linearized continuity equation, the momentum equation. Here's Poisson's equation. And then we assume that our perturbed quantities, these are the things that I've indicated with a prime next to them, have a periodic time dependence. And I'm assuming that the frequency of the time dependence is sigma, the angular frequency. We assume a periodic time dependence. We also assume that all perturbed quantities can be written as some function of radius times some function of angular coordinates, theta and phi. So this is a standard separation of variables. And in fact, the angular functions that satisfy the linearized equations are the familiar spherical harmonics. So for most of us, the only time we have to encounter spherical harmonics is when we're dealing with quantum mechanics of spherically symmetric systems like the hydrogen atom, or when we're dealing with multipolar expansions of electromagnetic fields, because we're working with Jackson. But they crop up here because we are solving a wave equation in spherical symmetry. So exactly the same mathematical physics applies. Once we've assumed a spherical harmonic angular dependence, we're left with just a simple differential equation that we have to solve that describes how the radial dependence of perturbations behaves. I'll discuss that in a moment. First, a brief reminder about the spherical harmonics. These are angular functions that are characterized by a pair of integers, the harmonic degree L that tells us the total number of nodal lines on the surface of the sphere, and then the azimuthal order M that tells us the number of those nodal lines that are great circles. And here is an example of spherical harmonics going from L equals 0 up to L equals 3. The positive M spherical harmonics propagate as traveling waves around the star in one direction. The negative M spherical harmonics go in the opposite direction. And this is essentially what is happening on the surface of stars, but I've greatly exaggerated the amount of motion and the degree of the temperature changes that arise from these oscillations. So let's go back to the radial equation. So it's a simple second order differential equation, and it involves some function f, and the behavior of solutions really depends on whether f is positive or negative. If we assume that the solutions change on a scale much smaller than the scale length over which f changes, then if f is positive, we have propagating wave-like solutions that are oscillatory in space, and when we combine that with that oscillatory time dependence, will actually look like traveling waves. Or if f is negative, then solutions will look like exponential decay or growth in space. And so what we can do, if we happen to know a stellar model and we happen to know what the actual functional form of f is, we can piece together these propagating solutions with exponentially growing or decaying solutions, the evanescent solutions, piece them together and make sure they match at turning points and apply appropriate boundary conditions and actually solve this equation. And it turns out that we can only solve it for certain values of the frequency. So the frequency is an eigenvalue, and this is actually a boundary eigenvalue problem. So I'm going to drag you all screaming back to a little bit of undergraduate quantum mechanics with a reminder that this is exactly the same problem we solve when we deal with the time-dependent Schrödinger equation for a harmonic oscillator. So in that case, the function f depends on the energy eigenvalue and the shape of the potential. This is a plot here of the parabolic, I guess I need to point it out with this, the parabolic potential associated with a harmonic oscillator. If we pick an energy, let's say this one, this dashed line here, where the energy is greater than the potential energy, we have an allowed region and we have wave-like solutions. Where the energy is less than the potential energy, we have an evanescent or forbidden region and we have exponentially decaying solutions. And we piece them together to make complete solutions. And in fact, that piecing together and applying boundary conditions leads to a quantization condition, that the integral of the square root of f, which is square root of f is essentially the wave number of the solution. The integral of the square root of f between the turning points where the energy matches the local potential energy should equal some integer number of half wavelengths. Basically, this is very analogous to waves on a stretched string that's clamped at both ends. We can only fit an integer number of half wavelengths on that string and simultaneously satisfy the boundary conditions. It's a bit more complicated here because we've got an extra phase factor, but for the n equals 1 mode, you can see we've got just half a wavelength, the n equals 2, 2 halves of a wavelength for a whole wavelength, n equals 3, 3 halves of a wavelength, and so on. So the mathematical physics underpinning stellar oscillations is exactly the same. We have propagation regions, we have forbidden regions, we can characterize solutions by counting the number of nodes in their wave function. This has no nodes, this has 1 node, this has 2 nodes, this has 3 nodes. The presence of boundary conditions means that we can only find solutions for certain values of the frequency, and that's essentially what gives rise to the star set of normal modes. The only wrinkle is in the functional form of f for stellar oscillations. For the quantum harmonic oscillator, the potential function is just this parabola. For stellar oscillations, it's a little bit messier. I've got an expression for it in the top equation here. And this expression depends on the frequency, sigma, of the oscillation, depends on the local sound speed, c. This is the adiabatic sound speed. And then it depends on a pair of quantities that have dimensions of frequency squared. One of them is the square of the Lamb frequency. The Lamb frequency is the frequency of a horizontally propagating but vertically evanescent acoustic wave in a stratified medium. The other characteristic frequency is the square of the Brunt-Weissler frequency, or buoyancy frequency. This is the frequency that let's say a fishing float will bob up and down if you disturb it. So it's the characteristic frequency associated with not sound waves, as the Lamb frequency is, but with buoyancy waves. And these are also known as internal gravity waves. They are nothing to do with gravitational waves. And until LIGO made its first discovery, the study of gravity waves was straightforward. And now Google is ruined for everybody working on gravity waves, because if you search for gravity waves, you will get gravitational waves. But these are gravity waves where the restoring force is buoyancy. They only exist in a stratified medium, so you don't get these gravity waves. For instance, if you're playing around with water in a fish tank on the International Space Station, because there's no stratification due to gravity. So if you remember from a few moments ago, I argued that solutions look spatially oscillatory wherever f is greater than 0, and they look evanescent whenever f is less than 0. So we can construct what we call a propagation diagram, which is the exact analogy of that plot I showed for the quantum harmonic oscillator. if we pick a frequency and draw a horizontal line of that frequency, regions where that frequency lies above both the Lamb frequency and the Brunt-Weissler frequency, or beneath both of those frequencies, will have a positive F, and I've shaded white here. The gray regions are where the frequency lies between the Lamb and the Brunt-Weissler frequencies, and those are evanescent regions where we won't expect propagation. So this is an example, this is the propagation diagram for a polytropic model. And so I'm plotting the function of radius on the x-axis, frequency squared on the y-axis. I'm plotting both the Brunt-Weissler frequency, which starts off small at the center and becomes large at the surface, and the Lamb frequency, which is infinite at the center of the star and drops down low towards the surface. And you can see there are two distinct regions where I can have wave propagation. One region is where the wave frequency is above both the Lamb and the Brunt-Weissler frequency, and those waves locally look like acoustic waves. And so modes that happen to be of a frequency such that they're up in that acoustic wave region and satisfy the boundary conditions are what we call acoustic modes, or P modes. P stands for pressure. Likewise, at low frequencies, where the frequency of waves is less than the Lamb and the Brunt-Weissler frequency, we also have another propagation cavity, and modes trapped in this cavity are known as gravity modes, or G modes. And in fact, the horizontal lines I've drawn on this plot show you the frequencies of this model's oscillation modes. This is for dipole modes, L equals 1. And on the horizontal lines, I've actually indicated where the wave function node is, where the wave function passes through 0 using a solid dot. The sort of orangey line is the fundamental mode that has no nodes. The first line above that is the first overtone P mode, P1 mode. The next line above that is the P2 mode, the P3 mode, and so on to higher and higher frequency. And then down at lower frequencies in blue, we have the G1 mode, the highest frequency G mode, and then we go to higher order G modes as we go to lower frequencies. Now this is actually a movie, so I'm going to play the movie now, and as I play it, we're going to change the polytropic index to make the model more centrally condensed, and you'll see how the frequencies of the modes change in response to the change in the Lamb frequency and the Brunt-Weissler frequency of the model. So the Brunt-Weissler frequency towards the center of the star is developing this big hump on the left-hand side of the figure, and that's really expanding the frequency range covered by the G mode cavity. And in fact, we've got a new sort of mode that's now appeared in our model, where in one part of the star, this mode behaves locally like an internal gravity wave, but in another part of the star, it behaves locally like an acoustic wave.
Real quick, so I don't get lost here. Which physical parameters started changing?
It's you could think of it as a measure of the central condensation of the star. So it's going from something that looks more like a uniform density star to one that's got a steeply decreasing function of density.
Oh, I see. So the radial density function as opposed to just physical size.
Yes, it's so all of the frequencies have been scaled to the free fall time of the stellar model. So the actual physical size of the star doesn't matter; it's how centrally condensed it is. In this sort of intermediate frequency region that I've labeled as mixed modes, in one part of the star, the modes behave like G modes, but in another part of the star, they behave like P modes. So we'll be coming back to propagation diagrams like this throughout the rest of my talk, because they really give a wonderful pictorial representation of where in the star we expect pulsation modes to be trapped and how we expect those modes to behave. But before we do that, let's just talk about the transition from helioseismology, which is oscillations in the sun, to asteroseismology, which is oscillations of stars. So there are 4 challenges we have to overcome when transitioning to studies of oscillations in stars. One of them is the sun. The sun is not conducive to observing stars. For obvious reasons, we can't really see the stars during the daytime. Clouds are also not conducive to observing stars because they tend to be opaque. The moon is very conducive to observing stars. Now, can anybody guess why? It's because everybody wants to do galaxies and they want dark time. So you can only observe stars when the moon's up, and the observing time is like trash to those extragalactic people. And they will let you have some of their precious telescope to point at a star. So you want the sun down, you want the clouds gone away, the moon has to be up or else the tack won't give you time. And then something that is really the biggest difference is that stars are a lot further away than the sun, and we cannot resolve the surface of a star. We cannot see waves propagating across a stellar surface. All we can see is the integrated light from all parts of the visible stellar disk, all sort of jumbled together. So we just have a point of light whose overall intensity changes, or maybe if we're lucky, we have a time-resolved spectrum for the star that shows some evidence of Doppler shifts on its surface. So what's really been a game changer that has allowed asteroseismology to take place is at least getting rid of those first three objections by putting our telescopes in space. So we can point them away from the sun. There are no clouds in space. Well, there's still some fighting to be done with tacks, but it's less to do with where the moon is. And it turns out in the last 15 years, we've been very fortunate in having many observatories put up in space with the express goal of monitoring the brightness of stars with high cadence, high precision, and long baseline. Now, the motivation for most of these observatories hasn't actually been to observe the stars themselves, but look for the small dip in brightness as a planet transits in front of them. But of course, they're still looking at stars for a long time, and it turns out these sorts of observations are an absolute boon if we want to study stellar oscillations. The sort of blooming of astroseismology has really been driven by the launch of these photometric monitoring satellites. It's also, I should be completely clear, it has been driven by the people interested in planets, because often we wish to know the age of a planet, or we wish to know its composition, or we wish to know whether it's in a habitable zone. And to do that, you have to figure something out about the star it's going around. So there's also interest in stars themselves from the planetary community. So this plot here is a Hertzsprung-Russell diagram showing you where in parameter space we can actually see stellar oscillations. So for the physicists in the audience, I'm going to bring you up to speed on this in the same way that maybe I had to drag the astronomers through the quantum harmonic oscillator again. This is to stellar astrophysics as the Feynman diagram is to particle physics and quantum mechanics. It is the narrative diagram that makes stuff make sense. It's not quite as powerful as a Feynman diagram, but it's still jolly useful. So it's just simply a plot of the positions of stars in a 2D plane, with one of the axes being their effective temperature, which is closely linked to their surface temperature and their color, and the other axis, the vertical axis, being the absolute or intrinsic luminosity of the star, just in ergs per second. We don't use watts, don't ask me why. Most stars in the sky are still in their hydrogen burning phase, where they'll spend most of their lifetimes, and they appear as a diagonal band on the Hertzsprung-Russell diagram that's traced by a red line labeled as ZAMs. After stars run out of hydrogen in their core, they end up in the upper right part of the Hertzsprung-Russell diagram as red giants. And then after they've run out of other sources of fuel in their core, they end up in the lower left part of the HR diagram as white dwarfs. Anything above 9 solar masses instead goes bang as a core collapse supernova, and that's far more exciting. But for the vast majority of stars in the galaxy, it'll start out somewhere on the diagonal line, move to the top right, and then move to the bottom left. And all of the circles, shaded or otherwise, that you see on this diagram are where we see oscillating stars. The colors are coded according to various criteria. The hatching patterns are coded according to various criteria, but we can do astroseismology on all of these different sorts of stars. So we can probe the internal structure of stars at many points during their lifetime. What I'm going to focus on in the rest of my talk are solar-like oscillators. So these are stars that are ostensibly like the sun, and the only real difference is we're seeing them from however many light years away rather than from 93 million miles away. The other sort of stars I'm going to focus on are a class of massive stars with masses between about 3 and 8 times that of the sun, called slowly pulsating B stars. So let's start off with asteroseismology of solar-like stars. This is the power spectrum of the oscillations observed in HD 52265. So I've got no idea where in the sky the star is. I don't care. I care about its power spectrum, though, because it shows evidence of having oscillations like those in the sun. These measurements were obtained by the Corot satellite. At low frequency, we see variability due to rotation of the star. There may be star spots that cause a low frequency signal. At higher frequencies, kind of in the middle, we see the signatures of convective granulation, those sort of cells that I showed you on that movie of the sun's surface. But then at higher frequencies still, we kind of see this excess power that here is labeled acoustic modes. And if we zoom in on that, we see a very characteristic picket fence-like power spectrum, where we have a series of discrete peaks that seem to have a uniform spacing, and we alternate between peaks that have a single spike and then peaks that have a double spike. So those of you here, this peak here is a single spike peak, and we have a double spike, and then a single spike, and then a double spike, and so on. And there's kind of a Gaussian envelope associated with the distribution of these peaks. And so just by looking at this, we can say, okay, there are kind of 3 things I can measure here. I can measure the separation between repeating parts of the pattern. So between pairs of single peaks or between pairs of double peaks. We call that the large frequency separation. I can measure the frequency separation between one of those double peaks, between the big one and the small one. And I can also figure out where in frequency units the sort of maximum power of this pattern is. So what I'm going to do now is try and untangle at least why we see the overall pattern of a single peak, a double peak, a single peak, a double peak. So to start on that sort of explanation, I'm going to show you a propagation diagram for a solar-like star. Actually, this is a model for the present-day sun that I calculated last night. And just as before, this is a graph of the 2 characteristic frequencies. The lower curve is the Brunt-Weissler frequency. The upper curve, the one that goes up to infinity at r equals 0, is the Lamb frequency. The shaded regions are evanescent regions. The white regions are where modes can propagate. And the modes that the frequencies that we observe when we look at solar-like oscillators are shown by the yellow band near the top. So clearly, we're looking at frequencies that will correspond to probably reasonably high order pressure modes. So these are standing acoustic waves trapped between the surface of the sun, surface of the star, and an inner turning point set by the Lamb frequency. So if we go back to our dispersion relation for waves and stars, and we make the approximation that the Lamb frequencies, the oscillation frequency is much larger than the Brunt-Weissler frequency, then we can get a simplified expression for f, and then we can apply our quantization condition that the integral of the square root of f between the turning points is equal to an integer number of half wavelengths plus some fudge factor that I'm going to call alpha. In the quantum harmonic oscillator case, it was -1/2. If I do that and I work through the math, I can get a formula for the frequencies of these p modes. And it turns out that the p modes have a linear frequency. So this is angular frequency divided by 2 pi, equal to some integer plus the harmonic degree, that's the spherical harmonic degree, divided by 2 plus 1/4 plus alpha. And this delta nu is basically a measure of the inverse sound crossing time of the star, how long it takes for an acoustic wave, a sound wave, to get from one side of the star to the other, going through the center. What's really interesting about this formula is it means that if I observe a sequence of modes that have consecutive n, they will be spaced apart by this delta nu, which depends on the sound crossing time of the star. And if I observe a sequence of modes with the same n but consecutive L, they will be spaced apart by delta nu over 2. So the reason why we have this uniform spacing in frequency is simply because we are in the high frequency limit of the dispersion relation in stars, and it just kind of drops out of the math. So if we go back to the picket fence, this frequency pattern, we can recognize that in the single peaks, those are actually dipole modes with L equals 1. The double peaks are a combination of radial modes with L equals 0 and quadrupole modes with L equals 2. And they're offset from each other by a very small amount because we've been a little bit sloppy in our analysis. If we go to a slightly greater depth in doing our mathematical analysis, we can actually explain that offset between quadrupole and radial modes in terms of the sound speed gradient near the core of the star. So we get a little bit of extra information out. And so a standard way of sort of extracting information from this sort of picket fence pattern is to create a frequency Echelle diagram, where on the x-axis we plot the frequency of each peak we see in our power spectrum. On the y-axis we plot the frequency. On the x-axis we plot the frequency modulo this large separation delta nu. And what it means, what happens when we do this is all of our peaks kind of stack up vertically in the Echelle diagram. So here are all the radial modes stacked nearly vertically. Here are the dipole modes offset by half of the frequency separation. Here are the quadrupole modes that nearly line up with the dipole modes, and they would if we did our analysis slightly more carefully. Now, in this diagram, the black symbols are the actual observations for the star, and the red symbols, the black filled symbols are the observations, the red symbols are the predictions of the best fitting model. And the fact that the points don't lie along perfect vertical lines, which they would if my formula was perfect, tells us that there's a lot more information to be extracted from the precise frequencies of these P-mode peaks than just that simple formula I gave you. And in fact, this is an example of forward modeling of a solar-like oscillator, where we construct a model for the star, we calculate the theoretically expected frequencies of the P-modes, and we compare that to observations. And if the two don't agree, it's clear something's wrong in our model, so we go back to our model and maybe using some knowledge of how different parts of the stellar structure affect the frequencies of modes, we can tune our model until it best matches observations. So this is an example of what happens when we use this forward modeling technique for 16 Cygni A and B, which it's a binary system with two stars that both show solar-like oscillations, and it's one of the best studied solar-like oscillator systems that we know of. And these are actually probability distribution functions for the radius on the left-hand plot and the luminosity on the right-hand plot of the two components, 16 Cygni A and B. So you can see that we know the radius and the luminosity of these stars to within, well, for the radius, it really is to within, a couple of percent. And this is what asteroseismology can do for us. It can really get us very precise measurements of both the global properties of stars we're modeling, but it can also even go further than that and start placing constraints on the microphysics going on inside the stellar interiors. So it has kind of revolutionized our study of stellar astrophysics into a 1% science when applied to specific individual objects. And what's made a lot of this possible, I don't mean to boast, but I am proud of this, is a pair of open source software packages that are used by probably over 50% of researchers worldwide working on forward astroseismic modeling. One is MESA. Sterl already gave the spiel, so I'm not going to go into it in great detail, but MESA stands for Modules for Experiments in Stellar Astrophysics. It's a stellar evolution code that can predict the internal structure of a star from its birth through to its death. And models produced by MESA can be fed into Gyre, which is my stellar oscillation code, and that will predict the frequencies of the oscillation modes in that model that we can then compare against observations. So in fact, throughout the talk, I've already included the Mesa and Jaya logos on a few slides. And when you see them again, that basically means this is some work that probably wasn't done by me, but that used Mesa and Jaya to actually do that asteroseismic modeling. So let's now talk a little bit about asteroseismic modeling of a different sort of star. So the solar-like oscillators, like the sun, have stochastically excited oscillations. These are randomly driven by the sort of the inherent sort of jostling stochastic nature of the convection zone at the surface of the star. Slowly pulsating B stars are quite different. They're actually an instance of heat-driven oscillations like Cepheids, but the heat driving works in a slightly different way, and the sorts of oscillations we see are quite different as well. So this is a typical light curve of a slowly pulsating B star as observed by Kepler. The vertical axis is in parts per million, so we're seeing variability. I'm just going to count the zeros. That's 60,000 parts per million, so 60 parts per thousand. So these are quite subtle variations and quite difficult to pick up from the ground. And we can see that the light curve certainly isn't sinusoidal. There's beating between many different oscillation modes here that's giving rise to this rather complex structure. And the typical time scale on which these oscillations are occurring is of the order of a day or so. And that's especially difficult to study from the ground because the day-night cycle really messes up your measurements. So I'm going to talk in a moment a little bit about what sort of asteroseismology we can do on these stars. But before I do, let me point out, as I said, that these are heat-driven oscillators like Cepheids, but the opacity valve that they rely on is not the second helium ionization valve. It actually depends on the opacity of iron and nickel. And there's a very pronounced peak in the opacity derivative at a temperature of about 200,000 Kelvin, which in these stars occurs about 5% of the star's radius below the surface. And this peak wasn't known about until the 90s, when updated opacity calculations came out of Los Alamos and the opacity project. So we didn't know why these stars pulsated until revised laboratory calculations in the 90s showed us there was this opacity peak that we'd been missing. So if we take the Fourier transform of the light curve and look at the power spectrum, but look at the power spectrum in period space rather than frequency space, we see a sequence of peaks that appear to be uniformly spaced, not in frequency, like we saw for the solar-like oscillators, but in period. And to explain what's going on here, we can go back to a propagation diagram. So this is a propagation diagram for a 5 solar mass star, about halfway through its hydrogen-burning lifetime. And as before, the curve, the lower envelope comes from the Brunt-Weissler frequency, the upper one from the Lamb frequency. Shaded regions are evanescent zones, white regions are propagation zones. And the frequency of the modes we see in SPB stars is very low, long periods of days. And it turns out these are actually G modes. So internal gravity waves that are made into standing waves by the boundary conditions. We can play the same game as we did for the solar-like oscillators by looking at how the dispersion relation behaves in the low frequency limit. And sure enough, we end up with a formula that predicts that the periods of G modes should be uniformly spaced as we go from one radial order to the next higher radial order. And the spacing depends both on the harmonic degree L, but also on some sort of average Brunt-Weissler frequency for the star. So this is the same power spectrum I showed you before, but underneath it is actually a plot of the difference in period between each mode and the adjacent mode. And you can see that the period spacing between adjacent modes is approximately constant as a function of the periods of the modes themselves at around 5,000 or 6,000 seconds. So I guess 600 seconds is 10 minutes, so 6,000 seconds is 100 minutes. Indeed, that's kind of what we see in this star, that the period spacing between modes with adjacent radial orders n is about constant. But there's a little bit of fluctuation, and that in itself is interesting. That's where the sort of extra information comes out. So we can actually use modulations in this period spacing as a diagnostic for the age of these stars. So in the left-hand panel, I have a plot of the period spacing as a function of the radial order n of modes for a model that's a little bit less than 5 solar masses, 4.21. And in the upper right panel, I've got a plot of the hydrogen mass fraction, the hydrogen abundance as a function of radius in the interior parts of the star, and in the lower panel, the square of the Brunt-Weissler frequency. And this is actually a movie. And as I set the movie playing, I'm allowing the star to age. The hydrogen abundance in the core is going down as it's burning its way through hydrogen. Just outside the core, we see the appearance of a trapezoidal-like structure in the Brunt-Weissler frequency, and that's caused by this chemically inhomogeneous zone where we have partially burned material, and the seismic fingerprint of this feature in the Brunt-Weissler frequency is a modulation in the period spacing. So adjacent modes don't all have the same period spacing. They actually follow kind of a cyclical distortion to that period spacing. So I'll play it once again because it's kind of a cool movie. So as the star evolves, the period spacing kind of gets more and more perturbed. And in principle, we can use that as a diagnostic for how much of the star's hydrogen fuel it's consumed as it evolves from the beginning of its hydrogen burning to the end. But there are lots of other cool things we can do. If I go back a couple of slides, you'll notice that these peaks kind of correspond to the dashed lines. The dashed lines show us a uniform period spacing pattern. But these peaks aren't single peaks, they're actually multiplets. And these multiplets exist because this star is actually rotating, and the effect of rotation is to lift the degeneracy of the mode frequencies with respect to the azimuthal order m. This is entirely analogous to the way the Zeeman effect lifts the degeneracy of atomic energy levels with respect to magnetic quantum number. And indeed, just as we can use the Zeeman effect to measure the strength of a magnetic field, we can use the rotational splitting to measure the degree of rotation in the star, and we can do it at different parts of the star. So we can actually do a measurement of the internal rotation at different depths within the star. So this is an example of the splitting of a dipole mode into a triplet, and this is a rotational inversion showing the rotation angular frequency as a function of position within the star, based on these sorts of measurements. This was our sort of first glimpse of what the internal rotation of a massive star might look like. And it was a little bit surprising because it looks like the interior of the star is rotating in the opposite sense to the surface layers. And I've got an idea on why that might be that I'll touch on at the end. Something that's being done extensively now with these slowly pulsating B stars is to take observations of them and see whether they can be used to constrain the sorts of mixing that are going on at the boundary of the star's convective cores and throughout the star's envelope. So this is from a great paper by Mike Pedersen and collaborators, where they observed, I think, 26 slowly pulsating B stars, and they saw which of 8 different models for internal mixing in the star could best explain the observations. And they found, kind of encouragingly, that there does seem to be a preference for one type of model. How this will impact the actual physics that goes into the models is yet to be seen. This is very recent results, but we're kind of at the point where we can do empirical tests of models for internal mixing that stellar astrophysicists have been arguing about for 40 years. So that's kind of exciting. So to finish up, I'm kind of near the end now. I'm going to talk about wave transport phenomena. So far we've seen the waves as an actor. We've seen waves and oscillations as an actor on the stage that is laid out by the structure of a star. They're just there to perform, and they tell us a little bit about the star, but they don't actually do anything to the star. But in reality, any of us who's been knocked over by a wave on a sandy beach and got a bit of seaweed in their mouth knows that waves transport energy and they transport momentum. They can trigger mixing and sometimes the removal of swimwear. And the same should be true for stars. I'm going to show you just a few brief slides showing some of the work that's done on wave transport phenomena where waves take an active role in shaping the evolution of the stars they're in. So this is from a, I think, 2, perhaps even 3D simulation, I can't remember, by Falk Kerwig of a 25 solar mass main sequence model. And this is a very massive star, 25 times the mass of the sun, that's burning hydrogen in its core, and the core is undergoing vigorous convection. And at the core boundary, these convective motions are launching internal gravity waves out into the envelope of the star. And these internal gravity waves have the ability to heat the star, to deposit momentum and angular momentum, but also to trigger mixing. And so in this simulation here, the convective region is this thing in the center that looks kind of sort of convective-y. And then all of these sort of twinkling striations are actually internal gravity waves driven by the convective core. And this is an empirical measurement of the mixing diffusivity from this simulation as a function of distance from the center of the star. This is the convective core, but just above the core, there's still a non-negligible amount of mixing by these internal gravity waves. And that could potentially alter the evolutionary trajectory of the star significantly by allowing the star to ingest more hydrogen into the core and prolong its main sequence lifetime. It would be callow of me not to include something from my hosts. This is actually a plot from a recent paper by Samantha Wu and Jim Fuller on the possibility that waves launched by very vigorous convective motions can actually deposit enough heat in the outer parts of a star to appreciably alter its structure. This is, in the top left, a propagation diagram for a star that's just ignited neon as a nuclear fuel in a shell around the center, and vigorous convection in this neon burning shell will send out waves that then get deposited, or their energy gets deposited near the surface of the star and cause the star to puff up quite considerably in radius and may lay the groundwork for some pre-supernova mass loss. I think Samantha and Jim found that there wouldn't actually be a sort of launching of material out to escape velocities, but certainly as soon as the star gets puffed up to 10 times its initial radius, there can be all sorts of secondary effects that come into play, like radiation driving, that may actually lead to pre-supernova mass loss. And that's a really interesting area of research at the moment. Now we have facilities like ZTF online and Vera Rubin's coming online soon. I'm going to finish with an animation that I kind of started making for that meeting where I crossed paths with Bob Christy, but only really got it to a point where I felt it was publishable almost a decade later. And this is thinking about not waves that are launched stochastically at a convective boundary, but by steady state oscillations of the sort we see in slowly pulsating B stars that persist for very long times. And I said, suppose we have a single oscillation mode excited in one of these SPP stars, and we just allow it to transport angular momentum. What will it do to the star's rotation profile? The amplitude of the wave is just set based on the observations. We observe these modes in stars at a certain amplitude. That's what I put into my simulations. So this is a plot of the angular rotation frequency as a function of radius. Within a very short time scale, and when I say short, I mean right now we're at the 10-year mark, so that's even younger than I am. This single oscillation mode transports angular momentum from the surface of a star and deposits it in the interior. And the starting point of this simulation was a star that was not rotating at all. So the overall angular momentum of the star has not changed, but the surface has been set spinning one way and the interior has been set spinning the other way. And you may recall from a few slides back, that's kind of counter-rotating profile is what we see in one of these slowly pulsating B stars. This is still kind of an early days result, but after 1,000 years, we've managed to spin the surface layers of a star up to a rotation rate that would be on the order of 50 to 100 kilometers per second. and in the interior of the star in the opposite direction. And there'll be all sorts of interesting secondary instabilities that will come out of this strong shear layer. So I think this is just a demonstration that based on modes that we see in real stars that we know are there, what they can do, unless there's some extra physics that we're missing at the moment that we put in there. As a final slide, I'm going to show a movie I generated last year that's based on work that I've been doing in the last couple of years, which is the sort of ultimate example of waves changing what stars do. So this isn't so much wave transport as wave-induced perturbations or modulation of orbits in a binary system. So this is actually an extension to my Jaya code that I've created with Meng San and Zhao Guo that allows us to study forced oscillations rather than free oscillations. And the forcing is coming from the gravitational potential of a companion. And this is an example of a heartbeat binary star, which is an eccentric binary that near periastron shows a kind of pulse-like signature. So I'll point to it when it comes up. Near periastron, you're going to see that's a heartbeat pulse like that, burum. And then away from periastron, you still see some kind of brightness variations that come. Okay, it's going crazy now. That come from the fact that you're partly resonantly exciting some of the star's gravity modes. So this is new functionality that I've added to Jaya that hopefully in the future may help us to do things like tidal asteroseismology, but also allows us to predict how orbits will evolve over time due to tidal effects. So let me finish up with an outlook for the community. Precision asteroseismology, 1% radii, masses, whatever, is now a thing. So stellar astrophysics is one of the oldest parts of astrophysics, and it's now got to the point where it's very precise and very powerful. Unfortunately, there's still a lot of catch-up work to be done on the theoretical side. We have partial descriptions of how rotation, magnetic fields, nonlinearity change the way things behave, but we're certainly not all of the way there. So people working on the theoretical side, like me, like Jim, like others, have our work cut out for us. And I think the next frontier in stellar evolution modeling will be to take all of these wave phenomena we're starting to learn about and put them back into our stellar evolution calculations. So that's what the community is going to be doing. For me, I finish up my stint as chair in August. I'm then going on sabbatical for 18 months. And I'm just going to take it easy, and I'm going to do that just by carrying on playing around with stellar oscillations, because they really are an absolutely fascinating topic for me, a source of great intellectual nourishment, and they're just fun. I don't care too much that astroseismology is great at getting precision ages. I just enjoy studying stellar oscillations. Thank you.
Okay, so time for one of these to question.
So you showed the period variation in the B-type oscillating stars in the G mode. This is effectively a fuel gauge, right?
Yes, absolutely.
Do you have any data on populations of these stars that you could plot maybe on the Hertzsprung local diagram and see if it actually tracks?
So probably not now, but a few more years of tests. Plus, plotting massive stars on the HR diagram is not easy because Gaia has some systematic problems getting their distances accurately. And ultimately, the major barrier comes down with how accurately you can put them on the HR diagram and determine whether they're near the 0 H main sequence or near the terminal H main sequence. If and when we crack that nut, we can absolutely do that fuel gauge thing, and we should be able to see their fuel tank running out as they evolve across the main sequence.
I'd just like to say that I've looked at all of these fields at the beginning of my career, and I'm speechless what you've done since then.
Cool. Thank you.